Let us discuss now the conditional probability density function. Analogous to the discrete random variable, bivariate discrete random variable, here we will discuss for the continuous bivariate random variable, for y and x are both continuous random variable, how conditional probability density function of y given x equal to xi can be found. So, here these definitions are given. Conditional probability density function, if xy is a continuous bivariate random variable with probability density function, joint probability density function f xy of xy, then the conditional probability density function of y given x equal to x is defined by this relation, and for also for conditional probability density function of x given y is defined by this relation. Also the properties, it is very similar to the conditional probability mass function. So, let us write down it. Let xy be a continuous bivariate random variable with the joint probability density function. Here we will talk about joint probability density function, because they are continuous. Instead of probability mass function, we will discuss joint probability density function f of xy and marginal probability density function of x is f x x and the marginal probability density function of y is f y y. The conditional probability density function P.D.F of, suppose we are talking about y given x is equal to some point x, is defined by y given x. Very similarly, we will define when we define the probability mass function cases, here it will be joint probability density function by the marginal probability density function, marginal probability density function of x. So, provided here we assume that this is not equal to 0, and the conditional probability density function the conditional probability density function P.D.F of x given. So, this is even x equal to x given y is equal to some value y is defined as f of x given y, the joint probability density function by the marginal when f of y not equal to 0. So, this is the definition of conditional probability density function. Now, some of the properties are very similar to the discrete cases. So, because it is a probability density function, so for any values of suppose y, one property is that because it is a probability density function, so y given x, so let us write down one of the density function y given x should be greater than equal to 0, and also if you take the for a fixing x for any values of x, y given x dy minus to plus infinity, because it is a density function, this should be is equal to x, where x will be belongs to the range of, because otherwise f x x will be 0. marginal density function. So x has to be inside x, then only this is defined, and this integration will be is equal to 1. So for the other cases also it will be similarly it is defined. So it is very similar to the discrete cases. It is for the continuous cases analogous to the discrete. The definitions are for continuous cases. Let us do one numerical example using the probability density function to find for the bivariate continuous random variable. So this example it is given. The joint probability density function of a bivariate random variable xy is given by this. So let us write down this. The joint probability density function, the joint probability density function of xy. So a continuous bivariate random variable xy is given by f of xy. This is equal to some constant k whenever 0 less than y less than equal to x less than 1, and this is equal to 0 otherwise. This is equal to 0 otherwise. So actually it is non-zero in a domain y less than equal to x less than 1. So if you draw the graph here, suppose this is 0, this is 1, this is also 1. So this is 0 1, this is 1 0, and this is, so this is, so this is 1 1. Now if you draw this line, so this is nothing but x is equal to y is equal to x line. So now y is less than equal to x. Where y is less than equal to x? In this region, because here y is equal to x. So this region actually y less than equal to x. So it is a uniform distribution whenever in this region. So what is the area of this region? So this region should be 1 by 2 or half of this square. This is, so 1 into 1. So this region I think 1 by 2. So this should be 1 by 2 into 1 into 1, the triangle. So this will be 1 by 2. So now k value we have to find. So determine where k is a constant, determine the values of k. So now it is a probability density function. This has to be greater than equal to 0. K cannot be negative. It has to be greater than equal to 0. And how we will find the values of k? So because by the properties of the density function, integration minus infinity to plus infinity, minus infinity to plus infinity, f x y dx dy, this should be is equal to 1. Now this function non-zero only if y less than equal to x less than 1. So y can goes to, so this is which implies now y can goes to minimum 0, maximum. So if you do integration of y first, so then limit of y can be written 0 to x, or you can write the other way also, and then this is k constant, this is first dy, and x can go 0 to 1. So I just want to do the y first. So any value y, if you put particular values of fixing the values of for the limit of y. So limit of y will be, so here it is given y is between 0 to, so y minimum value for a particular value of x. So the y limit will be this is, so the 0 to up to x, 0 to x, and then x limit can be anywhere between 0 to 1. So then this integration will be k, because I just changed this integral because it will be simple little, otherwise this value will be same. So this is nothing but x dx integration 0 to 1, because integration this is limit 0 to x. So x, this is equal to 1, which implies k into x square by 2, this is 0 to 1, which implies x square by 2, if you take the limit 1 by 2 only, k into 1 by 2, this is equal to 1, which implies k is equal to 2. So our value will be, so this area is 1 by 2 actually. So finally the joint density function of x y, the joint probability density function of x y is given by, this is equal to 2 whenever 0 less than equal to 0 less than y. So, we can make y less than equal to also less than 1. So, because it is a continuous random variable. So, whatever it is given, just we are writing here 0 otherwise. So, this is the joint probability density function. We found that k is equal to 2. Find the marginal probability density function of x and y. So, we have to find the marginal probability density function. So, the marginal probability density function of x is given by definition f(x)(x) is nothing but minus infinity to plus infinity f(y)(y) dy, but f(y)(y) sorry, it is joint density f(x)(y) xy dy. We have to do the integration of joint density function with respect to the other variable to find the marginal density of the x. So, now this joint density function, it is non-zero whenever in this region. So, in this region for x between 0 to 1 any value, y can go 0 to x. So, here this limit is given. So, it is straightforward. So, this is nothing but it is 0 to x. So, we will write here this is equal to for 0 less than x less than 1 f(x)(x) is nothing but 0 to x k is 2 to dx. So, this is nothing but 2x. Hence, the marginal probability density function, the marginal probability density function of x is given by f of x is equal to 2x whenever x is greater than 0 less than 1. For any other value, this density is 0. So, this is 0, integration will also be 0. So, it will be 0 otherwise. Now, we want to find the marginal probability density function of y. The marginal probability density function of y is given by f of y, by definition it is minus infinity to plus infinity f(x) y x comma y dx. So, we have to do only dx because y you want to find, we have to do the integration with respect to x. Now, for y less than equal to less than 1 greater than 0, as it is given this value f(y) is, so we have to find the limit. So, here this is non-zero whenever 0 less than y less than equal to x less than 1. So, limit of x will be y to 1 for a given y. So, we have to find the limit of x. This is nothing but y to 1 f(x)(y) is nothing but 2, it is constant dx. So, this will be nothing but 2 into 1 minus y, otherwise this value is 0. Hence, we will write the marginal probability density function, of y is given by, hence the marginal probability density function of y is given by f of y is 2 into 1 minus y whenever y is between 0 to 1, and this is equal to 0 for any value outside the region 0 1, this will be equal to 0. So, this is the marginal probability mass function. Okay. So, now question is that find this. Okay. So, find probability of 0 less than x less than 1 by 2, comma 0 less than y less than 1 by 2. Let us do that. Probability of, so this density function, so probability that 0 less than x less than 1 by 2, 0 less than y less than 1 by 2, 1 by 2. So, this is by definition 0 to 1 by 2, 0 to 1 by 2, f x y, x y, dx, dy. But this function is not non-zero over the whole region. So, let us check that. So, if you draw this graph, suppose this is 0, 1, this is 1, this is 0, 1, this is 1, 0, then this is 1, 1, then this density function is non-zero inside this region. So, this region. Now, if you take this half, half is here x 1 to half 0 and y here. So, this is 0 half. So, then we have to do the integration over this region. So, this area will be proportional to 1 by 2 into 1 by 2 by 1 by 4, 1 by 8 actually. So, that is why we have to find. So, now this will be nothing but this density function will be 2 dx dy. So, first if you do, so let us for simplicity, because this density function will be for any value between 0 to half. So, this density function is non-zero in the region 0 less than y less than equal to x less than 1. So, this is given. So, this is the 0 y. So, this is equal to 2 in this region. So, let us take first limit of x y. So, then it will be little simple. So, just for computation purpose dy dx. So, this is equal to 2 whenever. So, x can go 0 to half maximum, because it is 0 to half, but for between 0 to half also for particular values of x, y can take up to 0 to x. So, then this is 0 to x, y can take. So, this is nothing but this is 2, this is y 2x, then dx, then 0 to half, 0 to half. So, then this is 2 into x square by 2, 0 to half. So, this is 1 by 2 square, 2 cancelled. So, 1 by 2 square, this is nothing but 1 by 4. So, this probability is nothing but 1 by 4. So, in this way, whenever joint probability density functions is given, we can find the probability. We have to properly find out the region, which region actually this density function is non-zero. So, accordingly we have to do the integration to find the probability. Now, the last problem, the last question is that find the conditional probability density functions of this is y given x and x given y, the conditional probability density function. So, let us by definition we have to find out. So, note that this random variable not independent. So, why? So, you can see that the joint density function is, it is a constant. So, this is a uniform distribution. Now, for f x is equal to 2x and f y y, it is 2 into 1 minus y. So, f y y is 2 into 1 minus y. So, obviously, f x y of x y, this is 2, which is not equal to 2x into 2 into 1 minus y in general, which is equal to f x into f y y. So, basically we find that f x y x y is not equal to f x into f y y for all x y. For all x y, it is actually no, it is not true actually. So, any particular values of x y, it is not equal to, then also it works. Hence, actually x and y are not independent random variables. Independent random variables. So, that is why the conditional probability density function, we cannot just say that this will be equal to the marginals. So, we have to find the conditional probability density function. So, the conditional probability density function of x given, suppose y is equal to y is by definition x given y, this is nothing but f of xy assuming that f of y non-zero. So, this is the definition. So, now note that this will be not non-zero for all the region. So, this is equal to, so f x y will be 2 whenever this will be y less than equal to x greater than 0 less than 1, and f y will be non-zero whenever y is belongs to 0 1. So, it is actually it is the given 0 1. So, for a particular values of y between 0 1. So, then what is the f y is, it is given 2 into 1 minus y. So, this is 2 into 1 minus y. So, this is cancelled, this is 1 by 1 minus y, and this is equal to 0 otherwise. So, just we again you can write for simplifying. So, the conditional probability density function of x given y, this is nothing but 1 by 2 into 2, this is how much, this is 1 by 1 minus y, whenever this is in this region 0 less than equal to x greater than y less than 1. So, now it is given y, we have to give the limit of x only. So, it sees that it is constant, whatever the x between 0 to y, it is 1 minus y, it is a uniform distribution for a particular values of y 0 1, whatever the value. So, it should not be equal to exactly 1, that is why this is open interval it is taken. So, this is 1 by 1 minus y whenever x is between 0 to y. So, it is 0 otherwise, this is 0 otherwise. Similarly, the conditional probability mass function, probability density function, the conditional probability density function of, it was x given y, given x equal to x is f of y given f of y given x, by definition this is f x y by f x x. So, this is non-zero when f x y equal to 2 whenever 0 less than equal to x less than y get less than 1, by the given the information, given the problem, it is open interval 0 greater than x less than y less than 1, this is less than equal to, so less than equal to y, and for x between 0 to 1. So, this is a density function of y given a particular values of x, and what is the f x x? So, f x x marginal probability density function of x, f x x here it is given f x x will be 2x. So, this is nothing but by 2x. So, this is 1 by x. So, this is 0 otherwise. So, now we can write down the conditional probability density function properly. So, this is nothing but f of x x, the conditional probability density function of y given x, hence the conditional probability density function, P.D.F of conditional probability density function of y given x, equal to x is f of y given x, this is equal to 1 by x whenever y is between x and 1. Yeah. So, y is between x and 1, this is 1 by x. Okay. I did. Oh, this limit is actually, yeah. So, that is why this 0 less than y less than equal to x less than 1, 0 less than y. So, I made this mistake, sorry. So, please correct this. So, 0 hopefully you have observed these things. So, it is actually just interchanged x and y in this 0 less than y, 0 less than y less than equal to x here, and here this is y, this is x. So, then finally we will get, so wherever it is 0 less than y less than equal to x less than 1, anywhere it is a mistake. So, just it is interchanged actually. So, here also we have to give this limit 0 less than y less than equal to x, where x between 0 1 any value it can take, then 1 by x. Similarly, here also this is 1 by 2 1 by g x between. So, here actually 1 by 1 minus y if 0 x is between y. So, we have to write like this, x is between y to. So, basically it is important what is the limit of x, x is between y to 1. So, that is why x will be 1 minus y whenever whatever, y will be one of the value between 0 to 1, it will be open interval 0 to 1, limit of x will be 1 minus y to 1. So, that is why it is 1 minus y, it is a uniform distribution in the range y to 1. Here it will be, this limit will be, if we finally write 1 by x whenever limit of y will be 0 to x, x belongs to 0 to 1, and this will be 0 otherwise. So, this is the conditional probability density function of y given x. So, this is the final answer. So, these are the questions it was given in this problem using the conditional probability density function we discussed now, and also the joint probability density function, how to do the compute the probabilities, related probability, their marginal probability density function, whether they are independent or not, that also we checked. In this case x and y are not independent random variables, and also we have found that y given x, though xy joint probability density function, it is a uniform distribution in this region, but the marginals are not uniform distribution, but the conditional probability density functions are again a uniform distribution in a particular region given x and y, those will be the uniform distribution accordingly. So, hopefully you have understood this example. So, next we will discuss some other topics. So, how two random variables we can measure their associations. Also, for bivariate random variables, univariate random variables, we have defined some of the moments, first order moment, second order moment, nth order moments. So, here how we can define the moments. So, that we will discuss now.